And then we move to the third talk in the session. And the third talk in the session will be given by Giancarlo Guizzardi of the University of Twente. And I must say that although we have been in contact in Twente, since we are both from Twente, I think we have never met in person yet, Giancarlo. So I think this is also the time that we should change that. But unfortunately now I'm in Louvain and you are, I suppose that you are in Twente now. So let's change that. Giancarlo has been working on the topics of ontologies, conceptual modeling, data and knowledge engineering for the past 25 years. He's worked on developing theories, languages, methodologies, and computational tools in these areas. He's been active both in academia and in industry, building reference models in many domains, including software engineering, energy, telecommunication, tourism, healthcare, fiction, agriculture, and various others. And two of his best known results are the unified foundational ontology and the modeling language OntoUML. So there are many aspects that Giancarlo will talk about, and I cite two of them because we are heading more towards also a formalistic approach into how to use ontologies also in the field of material science. And these are very deep statements, in my opinion, that I have not put my head around completely yet. But one of the statements will be that data inevitably embeds a theory of a portion of the world. And that is a very deep statement, and I'm sure that you will say much more about this. And the second statement that I also like very much, and I'm also very curious to learn more about, is this statement that the interoperability of FAIR is only possible if our data modeling languages, methodologies, and tools are able to reflect the true ontological distinction in the sense that you've defined previously. So I'm looking very much forward to giving your talk, and the floor is yours.
Thank you very much, Ton, for the presentation. It's COVID's fault that we haven't been able to meet in person yet. Let me share my screen. I think this was a good summary of the main points of the talk. So the talk is on the relation between ontology as an area, the area of formal and applied ontology in philosophy, ontologies as artifacts in the sense that Carlson was just telling us, and the I of interoperability in FAIR. Right? So we know that FAIR stands for is an acronym referring to these 4 different dimensions, and I'm focusing here on this notion of interoperability. It's important to highlight that the definition here of FAIR is recursive. So we say that an information artifact is FAIR if described by information artifacts that follow the FAIR principle. So an information artifact in the particular guise or focus of this talk is interoperable if described by artifacts that are themselves interoperable. And the focus here is on ontologies as these artifacts which describe data in this FAIR context. So what does it mean for an ontology to be interoperable? So first, a definition of ontology that I'm taking here is it's one of the original definitions of ontology, which is a theory about the kinds of entities and their ties that are assumed to exist by an information artifact, by a description of reality. So this is connected, for example, with the philosopher Quine, that underlying any description of reality, there is a commitment to a certain theory about the kinds of things that are assumed to exist. So in that sense, an ontology is not bound to a particular modeling language or description language. So my first point, and then the first takeaway message is that ontology in this sense is completely inevitable. Not only all descriptions make an ontological commitment, but in particular, all information artifacts, which have what is called real world semantics, which not just a piece of mathematics, make an ontological commitment. For example, this is an information artifact, the subway map of Vienna. And this thing makes an ontological commitment to a number of things in reality. So it believes that there are, stations and lines, and there are certain relations between stations in the line and certain, so some ordering relations between stations, some intersection relations between lines, and so on. So it commits to a given worldview in which there are these things. There are stations, lines, and relations between all these things. Any information system in particular does that. So if we take even the most mundane information system or a database, for example, this one talking about transplants, this thing believes that there are people and who can be living or deceased, and there are transplants, and there are these surgeons and donors and donees which participate somehow in a transplant and are somehow connected to a person, right? So this refers back to the very first mention of the word ontology in computer science, which comes from a paper by a guy called George Milley, the creator of Milley automata in computer science, in a paper called Another Look at Data from 1967, in which he makes this case that data is a theory about things which exist in the real world necessarily in order to be usable. And data processing is juggling these representations of this theory. And that's an issue of ontology in the words of Milley, by the way, referring to Quine again. So the opposite of ontology is not non-ontology, it's just bad ontology. You're gonna do ontology work anyway, because again, in defining information structures, you are making ontological commitments which are inevitable. So, but it's not just about, the ontological commitment is not just about recognizing the kinds of things that you take to exist, but recognizing what are the possible interpretations of this thing, of this information structure. So for example, there are interpretations, if this model is too loose, right, it doesn't have enough constraints, there are interpretations of this structure which are valid, but not intended. For example, relating this to, I'll explain this by a relation between these two sets. So given an information structure, there is a set of possible interpretations of that model, right? Valid interpretations given the set of constraints which is present there. And there is a set of intended interpretations of the model. And our job is to find in the correct set of constraints that would make the two sets match. So if there are missing constraints, I could have, for example, here in this portion of the model, have a possible interpretation of this model in which there are people who are neither living or deceased, or there are people who are both living and deceased at the same time, for example. Or that there are transplants in which the surgeon, the donor, and donee are roles played by the same person. In other words, I donate an organ to myself and perform the transplant, right? So this would be a valid interpretation of this structure, but it's not an intended one. So if models are under constrained, there are things in the set of possible things, possible interpretations which are not intended. If the models, for example, are over constrained, for example, if I decide that I will include a constraint here that will define these three things as disjoint, so no surgeon is a donor or a donee, I'm over constraining the model because now a surgeon can never receive or donate an organ, for example. So this is more than I want to say. I just want to say that they are roles which are disjoint in the scope of the same transplant, right? So if I have things which are, I have this situation, things which are intended but not possible, I'm over constraining the model. So the problem here is finding out the exact set of constraints that would make these two things meet. And this set of constraints is the specification of my ontological commitment. So in this sense, an ontology is a kind of contract representing a given worldview, a given conceptualization, telling the world what is my view about transplants and marriages and enrollments and employments and presidential mandates and so on, right? Telling the world which are the interpretations that I find acceptable. In other words, which is my worldview or conceptualization. Now, there is a practical inevitability, so it's impossible to avoid doing ontology work, and it's impossible in practice to avoid dealing with this problem of interoperability. Why? Because all questions that we want to have answered in government, in organizations, in science, and so on, can only be answered if we put together data silos which have been developed in a concurrent, autonomous way. And connecting these data silos is connecting the different worldviews which are embedded in the information structures of these different systems. So the problem of interoperability is exactly the problem of relating these different worldviews. Semantic interoperability, therefore, is a problem of relating these different ontologies, relating these different theories, which are embedded in the systems. It's finding out, for example, the relation between person on the left side and person on the right side. Can I assume that this is a relation of identity just because I'm using the same lexical term? Or transplant on the left and transplant on the right? If not a relation of identity, then what kind of relation do I have there, right? Can I have there? Dependence, what kind of dependence? Historical, existential, generic dependence? If not dependence, then what? Specialization, parthood, what are the possible relations between these things, right? So in order to articulate this possible relations, I need a kind of conceptual toolbox. I need a vocabulary and a toolbox with notions talking about identity, about dependence, about parthood, about causality, about events and participation of objects in events, and such that I can articulate these relations, because this is a prerequisite for encoding these relations in the particular connections between the artifacts inside this information system. So for example, if I know this is a relation of identity, I can code the axiomatization of identity in the representation of this reference in these information systems, right? I know an identity is an equivalence relation and it obeys what's called Leibniz law. So if two things are the same, they have the same properties and so on. But I can only code that, formalize that, axiomatize that if I know it's a relation of identity I'm talking about. So this toolbox is exactly what's provided by ontology now with a capital O. So ontology as an area devoted to developing this domain-independent toolbox with tools for supporting this kind of ontological analysis, right? So it's a 2,400 years old discipline, or that provides theories and tools and methods of doing this kind of analysis. And just to give you some examples how this can get tricky very, very quickly. So take this notion of service, right? This seems to be, I'm going to use three examples which are seem very intuitive. So we seem to have a very strong grasp of the semantics of terms like this. So when we say a service, do you mean the service offering, like Vodafone says that you can hire a telecommunication service for a particular price and certain conditions? Do I mean a service agreement, which is a contract between Vodafone and a specific user? Do I mean the process of service negotiation? Do I mean the process of service delivery? Do I mean the description of the contract, of the agreement, or of the offering? These are all different ontological types of entities. Ontologically different types of entities. So the first one is a kind of relational complex, bundles of commitments and claims. So is the second. The third and the fourth are types of events. The fifth one is actually a normative description. What about software? Do I mean software code? Do I mean a software program? Do I mean a software system or a software product? It turns out that these things, the relation between all these things is not one of identity. So for example, the identity of a software code is a synthetical thing. So if I rearrange the code, I modularize, I include comments, I have a different code, but I still have the same program because the identity of the program is defined by the execution class, right? While I can change the execution class of the program and still have the same system because the identity of the system is defined by a set of requirements. It's in that sense that we say that Microsoft Word has 40 years old these days, right? It's not the same code at all. It's not the same class of execution. It's just the stability of a set of core requirements. It probably doesn't even have one single original line of code there. And the product is it's not even that thing at all. A product has to do with those commitments and claims. Again, it's a time of product agreement. So when Microsoft buys Skype, it's not buying code. It's buying the rights and obligation with respect to a base of users. What about person? Do I mean a human being Do I mean a cognitively capable human being with a legal sense of person, in which if I'm brain dead, I'm not a legal person anymore? Do I mean a legally recognized human being? So the thing that we become when we are registered and recognized by a certain jurisdiction? Or do I mean a legal person in the sense that would include also organizations? So institutions as legal persons, things that can participate in legal relations. These are all different types of types. A human being is a kind, so a type that things instantiate necessarily and that define essential properties of those instances. Cognitively capable human beings is what is called a phase, so it's a contingent type that things of the human being kind can instantiate contingently. Legally recognized human being is, again, a type contingently instantiated by human beings when establishing relations with certain jurisdictions. And legal person in the fourth sense is not, it's a type that classifies things of multiple kinds, namely the kinds human being and institutions. So we need, again, this toolbox. And once we have this toolbox, we can safely reason, identify, analyze, and therefore encode this kind of relations. This is important when we are putting systems together, because remember, without the proper set of constraints, and therefore with a deviation between the set of possible and intended models, we can have what is called the false agreement. So two systems which intersect in their possible models without intersecting in their intended models. So this is the worst case, the worst problem that we can have with interoperability. It's not a problem if we disagree, it's a problem if we falsely believe we agree. So what is also inevitable, therefore, and that's the point I'm defending here, it's inevitable to make use of ontology in the capital sense, to make use of this toolbox and this series and these methods and this vocabulary for reasoning with how to model things and how to establish distinctions, connections between these different ontologies in the lowercase o sense. Now, let me be a bit fair with FAIR. The FAIR original paper defined these three requirements related to interoperability. I basically touched this one, I2, saying that it's recursive, and this, if we figure out how to articulate these different worldviews and find out how to make qualified reference between these different models, we address this third requirement. But now I would like to come back to this one. So what kind of language do we use to create these artifacts, these ontologies with lowercase o? What I'm defending here is that this task is much facilitated if we have a language that incorporates in its primitives, in its modeling primitives, exactly those ontological distinctions that we use to make those process of ontological analysis, right? So in other words, if we have a language, a modeling language, it's not ontologically neutral. So what kind of language would fit the bill? So the claim is first order logics wouldn't be the case because of its higher ontological neutrality. So logics would allow you, it's neutral in that respect, or much more neutral in that respect, and would allow you to do whatever you want, to describe basically whatever you want. It doesn't impose any ontological restrictions. And it is the same case for OWL, for example, for the ontology, for the web ontology language, because it's basically a subset of first order logics, right? So it's neutral also in that respect. In a sense, the ontology in web ontology language is a misnomer because it has absolutely no ontology in the capital O sense in there. So a language that would honor these distinctions would code, for example, in its syntax and semantics, these ontological notions. It would make a difference, for example, between a kind like person and phases like living person and deceased person, and roles like surgeon, donor, and donee, and existentially dependent entities like transplant, which can only exist if there are entities playing the roles of surgeon, donor, and donee. And would also allow us to identify the relations between these different representations. So I could know immediately that person on the left cannot be identical to person on the right, the types, because they belong to different ontological categories. And the same here, that event on the left is a kind of event, or maybe a kind of relational complex as well. And event on the right is actually a type whose instance are types of events, saying that surgeons are habilitated or permitted to perform types of events. So the relation here wouldn't be, again, one of identity, but one of instantiation. In the previous case, it would actually be one of specialization. Right? Once we have that model and we have those connections between models, then if the formalization or the axiomatization of these structures can be generated systematically, if not automatically. In fact, from that model, we can generate several different encodings for the model using different formal language, OWL, for example, or first order logics, but other things, higher order logics and so on, satisfying different sets of non-functional requirements in these representations. Now, one thing which is quite important is that if you have a language that commits to a given ontological theory, what happens, or in other words, a language that breaks with this kind of ontological neutrality, what happens is that immediately patterns and anti-patterns emerge in this language. So the primitives of the language become design patterns as opposed to low granularity things like class or attributes and relations. So for example, if I know that a transplant is an event, I know that an event must have participants, often playing certain roles, that it happens in time, that all its properties are immutable, and so on. So when I instantiate that, I instantiate a cluster of concepts with a predefined axiomatization, a kind of theory inclusion mechanism. I can also identify certain anti-patterns. So if I have something like a transplant, an event in which I have several roles that take their identity from the same kind, of course, one possible interpretation is that the same individual of that kind would play more than one role. And then we can identify this automatically and suggest to the modeler a rectification for this error-prone structure in the model. So just to wrap this up, what I've been doing and my research group has been doing for the past 20 years, let's say, is to develop a foundational ontology, so a domain-independent set system of different micro theories dealing with many of these different ontological aspects, like, you know, classification and taxonomic structures, partial relations, different types of relations, causality, these higher order structures in models, dependence, events, and so on. And then develop a number of engineering tools coming from this theory. So in particular, a modeling language called OntUML, which is a well-founded extension of UML, for example. So it's a version of UML such that the modeling primitives reflect these ontological distinctions and that the grammar of the language has syntactical constraints that reflect the ontological axiomatization. So the language would proscribe from being syntactically correct the models that go against the axiomatization of the underlying ontology. And then we have, you know, computational tools for generating code, again, in many languages, like as I said, OWL, but relational database, Smalltalk, and Java, and many different things. We have tools for formal verification and validation of these models. We have tools for complexity management of large models, and we have tools for learning constraints from the result of validations of these models. So here's the takeaway messages. Real-world semantics implies an ontological commitment. So if we have any information structure and any system which is based in a certain information structure, which has meaning in the original sense of the term meaning, not just mapping a piece of mathematics to another piece of mathematics, but mapping to things in the real world, this thing makes an ontological commitment, and that's unavoidable. Semantic interoperability is about connecting ontologies, because the ontologies are, because of the first reason, ontologies are always there. So your system defines an ontology, even if you're not aware of this, if it has real-world semantics. So semantic interoperability, it's about connecting these ontologies with the lowercase o. And I don't think this can be done safely, that you can have semantic interoperability in critical systems and in critical cases without the proper engineering support, which is ontology-based in the capital O sense. So the slogan is no ontology without ontology. So no artifact, ontological artifact, no theory about the things you take to exist in a given domain without the support of ontology as this area, this method of analysis. That's it for me for today. Thank you very much. And I'll be happy to take questions now.
That was an impressive talk that you gave, Giancarlo. And basically, I would like to come back to you and ask the same question also to Karsten. Because in your presentation, you made an important statement. And you said that there is nothing like a bad ontology. You only have ontology or no ontology. If I relate this to material science, and it is somewhat of a joke, but I'm very, very serious about this. If I go back to material science, there is no difference between a solar cell material and no solar cell material. All materials are solar cell materials, and the only distinction is between a good solar cell material and the bad solar cell material. Right? I can make any material, not any, but many into solar cell materials, but we are optimizing things. And for this, that seems to be a quite different type of use for ontology than the way in which you are phrasing your ontologies. So let me go back first to Giancarlo. What do you really mean with there is no difference between ontology and bad ontology? It's only a difference between ontology or no ontology. Can you?
Tom, I actually said the opposite of that. What I was saying is that there is, every time you create an information structure that has real-world semantics, you are doing ontology work anyway. So there is no non-ontology. There's just sometimes bad ontology, right? So if you're creating this database of transplants, you are committing to a certain worldview of transplants. So you wouldn't want to have in your database a transplant that happened, for example, before the transplant, the donor and the donee were born, for example, right? Or you wouldn't have in your database a transplant that, that is performed by the donor. So the donor, the donee, and the surgeon are the same people, right? Are the same person. So you wouldn't want to have that. But how do you know that's bad data? It's an issue in the end of data quality, right? But you can only judge that that's bad data because you have a theory of what are the constraints that exist in the world in the domain of transplants. So you are doing this anyway in building your database and your application and the connections of database and application. You are articulating an ontological theory, a theory about the kinds of things which exist in the world. So you cannot help doing that. But sometimes people, by doing that without the proper tools, they will have bad ontologies or bad articulations of what exists in the world. So there is, what you cannot avoid is doing the ontology work. So the opposite of ontology is not no ontology, just bad ontology.
Some related question actually comes up in the chat, because in solar cells, which have been mentioned a lot during this meeting, it is not only about static properties, but it's also about dynamic properties, about transport or response functions. So here in the chat, Rafa Ritz mentions importantly, how do you express dynamic aspects? So events of type A typically precede events of type B, or including the notion of time and evolution?
Yes, that's a very, very important question. So we have in this UFO ontology, one important fragment of the ontology is an ontology of events, which is called the UFO-B, in which we deal with several different aspects of events. So we have, the temporal relations between events. We have causal relation between events. We have this notion that events change the world, mapping situations to situations. You have a mereology of events or parthood of events, which is a particular theory of parthood. We have the theory of object participation in events, and we have a theory about the relation between events and modality, this idea that events only have essential properties. So events are immutable, right? They cannot change in any way. They are changes, but they cannot change, although they can have properties. So for example, a presentation can be exciting or boring, but if a presentation is sometimes boring and sometimes exciting, it's because there are different temporal parts of the presentation which are boring or exciting. So we have this theory of events. And again, this is something which we brought to the language. So this modeling language also has a number of notions or primitives for actually modeling event relations. And again, you can generate code by following this axiomatization. Now, regarding time, if I still have time to answer this, and time is...
we continuously go into the discussion phase. So please, because I think it's very important, let me broaden the discussion, but please continue your answer. But the idea of this discussion is to see how we can optimally use ontology in the field of material science.
Yes.
That is the broader goal of this discussion also.
Wonderful. Thank you. So, for example, when I start doing this, I think the question is very interesting because often in the past, people did not represent at all in this kind of structure models, right? So in the tradition of conceptual modeling or information modeling in computer science, events would either appear in separate models like business process models or state machines or things like that, or they were entities which were not first-class citizens in structural models. I mean, we would model operations in all those types, just telling what kinds of things can happen to those entities, but without representing the events themselves. Of course, we need to represent the events because events, they have their own properties. They form taxonomies, taxonomic relations, and all different types of relations, right? So we wanted to take this theory of events that we had and embed this in our structural models. However, once we did that, we realized that would completely change the semantics of the models, right? Because, for example, so if I have this talk, imagine if I include this talk in my model, in my database, right? Once this talk is there, I have to be there because the talk is existentially dependent on me. It's my talk. So what happens to the model is that you immediately move from a kind of snapshot semantics of the model to a historical semantics of the model. And this propagates to the entire model. So this changes these structural models in non-trivial ways. And this corresponds to a particular view of time, which is what's called the growing block view of time. So this idea that time, so the future doesn't exist, but everything which happened still exists in a sense, although it's not present. So this has interesting implications. So for example, my grandfather somehow still exists because he existed in the past. So he's not present here today, but he can have causal effects in the present. For example, suppose my grandfather was Dutch and I want to apply for a Dutch citizenship based on the fact that he was Dutch. So my citizenship, which is an object which depends on me, is also existentially dependent on his citizenship, but his citizenship is dependent on him. So in order for my citizenship to be created in the present, it has to rely on the causal effect of his citizenship, which must still exist, although he exists in a different form. So this is an example of a non-trivial interaction between taking a serious theory of time and how this interacts with both dynamic and structural aspects.
Thank you. Maybe Patrick, you are also somewhat hidden in the screen. Would you like to comment on this one, also on the aspect of events and evolution of time?
Maybe I will just take up something else, which I think has some some relation to this. I've heard sometimes somebody say that there are different kinds of people working with ontology. I've modified a little bit. Said first, there are the philosophers. I think Giancarlo is one of those. Also, Achille Varzi and Nicola Guarino are people in this field, where the idea is mainly to represent the real world and really look at all these ontological commitments. And I think what Giancarlo is telling us here is very important. And it helps us when we are developing upper level ontologies so that we understand what is really going on. And I think in the material science field, you see people from EMO are trying to do this. The second kind of people are the computer scientists or maybe knowledge representation people, which probably I am part of, where we are mainly interested in knowledge representation, which kind of languages can be used, which kind of constructors to represent things like and, or as a logical constructors. And we're interested in, depending on which constructors you use, what is the complexity of the languages? So how much time will it take to do reasoning? And then there are the application people, domain expert people, for instance, material science people, who actually don't care of any of this. They have an application in mind and they just want it to work. And they don't care what how it is represented and what the connection is to the real world maybe. Now, what is interesting there is that for the computer scientists and for the philosophers, it may be interesting to know what are the tasks. So if you want to use ontologies in material science, what are the tasks that the application people need? For me, it is search and integration. That's what I'm working on. But it may be other kinds of things like defining similarities, clustering different materials, where you also could use the ontologies, for instance, in ontology-based machine learning. So for getting back to the events and time, I think what Giancarlo is telling us here is interesting for definitely for the upper level ontologies to which we can connect our own ontologies. And oh, I lost it. Okay, I'll stop there.
Yeah. Thanks, Patrick. And maybe also Karsten can give his worldview on this.
If I can comment very quickly, I basically agree with everything that Patrick said. I think these are indeed three different areas of concern. I think they are strongly connected. I'm myself not a philosopher, although I do a lot of this work with philosophers, but I started my career as a protocol engineer, implementing network protocols and working with process algebras and things like that 25 years ago. And I just thought it was extremely useful to look at this tool. So I think I'm between the two groups, Patrick. I'm very concerned about these ontological things in the philosophical sense, but I'm obsessed with creating engineering things and testing applications. But I fully agree with you with the characterization.
Then I give the word to Karsten to give his view on this topic.
Well, I'm not sure how qualified my view on the topic actually will be. But what I see as a problem in let's say of acceptance of this ontological approach in the field is that it seems like a very long run until one can actually get something useful out of it, right? So it's like walking through a desert is a bit, and the oasis where we get then the cool results is a bit distant, yeah. And also I think technically, what I find a bit annoying, for example, is that I can't really do a calculation with an ontology, right? I mean, many of the properties that we find interesting are derived properties. So the ingredients are there, yeah, but I still need to use at least in my understanding, an external tool to do such a analysis computation. So I think we are discussing a lot about very complicated high-level things, but some of the practical things would also be of interest for the community. So it's I think it easily gets a bit too philosophical, I would say.
Can I comment on that?
Please.
So how can we decide if things are too philosophical, right? I think they are extremely practical, actually. There is something that Patrick mentioned, this idea that, for example, my concerns are about modeling the world. I would like to emphasize that I don't think the role of ontology, even philosophical ontology, should tell people how to force people to agree in a certain worldview, right? I don't think that's possible. I think people look at domains with different interests and in different granularities and so on. What we want to do is to provide tools that would help people to have a consistent view within their set of choices. So a kind of intra-worldview consistency and inter-worldview interoperability. So you model your thing in a consistent way and find out how your worldview relates to other worldviews. So it's not about being normative in the sense of telling people how the world should behave, right? Although some philosophers do that. I think it's extremely practical. So if you find out, for example, if you have a small theory of events, this theory of events with its axiomatization becomes a kind of design pattern. So every time you have to model events, you just reuse that thing and you guarantee a certain uniformity of both modeling choices and axiomatization. You can, it's like a pattern language. Sometimes you're going to include or exclude some of these axioms. So there are several, let's say, variation points, but you can reuse the bulk of the theory. The third point I would like to mention is that on calculating with things, there are different calculations I want to do with things. So for example, one of the mappings we have from this ontology, from this modeling language onto ML is to a language called Alloy that allow us to do model finding, type of visual model checking, right? And this is extremely useful for doing validation, which is very different from verification. So if I map this to DL, for example, this allows me to check satisfiability and a number of properties of the model, consistency and so on, but it doesn't help me much to check. So it allows me to check if I got the model right, but not if I got the right model. And validation by visual simulation can help you to do exactly that. So what this tool does is, for example, once I have that model about transplant, it's generating all logical models of that specification in a bounded context and so on, but a finite set of models. And one of those will be one in which I'm playing all these three roles in the transplant, right? Or that someone is playing two of these roles in the transplant and so on. So there are different calculations we want to do, and this with different non-functional requirements. Sometimes I don't care about decidability, for example, at all. I just want to do different things do different calculations, and this would require different language. But the conceptual understanding should be, I think, in my view, common to all these mappings.
Let me add my own perspective on this one, because I had been working on both solar cell materials and on these organic, inorganic hybrid systems, of which we've seen so many beautiful examples of, for many years. I have never thought that these materials would become solar cell materials. So if the ontology of this class of solar cells would have been correct, I should have known 10 years ago that these are important for solar cells. And I mean good solar cells, not the bad solar cells. And I missed this completely. So in my view, ontology would help also to see which materials are useful for which properties based on a larger database than just electronic structure calculations. So this was the reason that I also gave the examples that I gave in the beginning. I think symmetry is a perfect ontology. It is defined, it is clear cut, it's easy. but materials are infinitely complex with infinitely many possibilities. So then the question is, how do you use an ontology properly? Of course, you can use it to optimize a property, but also to see if materials that are developed in one area of research could be useful for catalysis or for anything. My personal statement, at least. Patrick, could you comment?
Yes, I agree with that. I can also comment on Karsten. I give a slightly different answer than Giancarlo because I interpret computation in a different way. So what Giancarlo was telling is about ontologies and the computation that you can do with the ontologies. And I agree completely with that because the ontologies are somehow a representation of knowledge. Now, if I would interpret Karsten's question as computations related to materials, then this is not what ontology would do. They don't compute these kind of things. The computations are about knowledge. So what you would be able to do with the calculations is to represent knowledge about these calculations. You could represent which kind of method you used for this calculation, connect these to other kinds of methods, connect to different kinds of methods that have been used to calculate the same kind of property or of different materials and so. So the computations for material science are maybe not the things that you will be able to do with ontology, but you can represent knowledge about these computations. And then the computations that you do for the ontology are the ones that Giancarlo talked about. Talking about, for instance, validation and consistency and so.
Karsten?
What I try to refer to is, in the end, the idea of, I mean, I do query using Sparkle as a language, so to say. And it would be super cool if I could do a little bit more complicated math in Sparkle. Yeah, if I could do such a thing, like we have this this Tanimoto coefficient. If I could compute such a thing as a Sparkle query, that would leave one step out that I have to do otherwise before. Yeah, that's just a practical thing. Yeah. But I understand that it's probably beyond the tool. So, and it's okay.
Well, you could imagine that you have information in the ontology about this coefficient, and sorry, you have information about the provenance information that I talked about before, where we would store information about which exactly algorithms or which tool that you've used. And maybe you can store information about the code there.
And that would exactly go towards this. I mean, I had these two questions in on this one slide, and the last one was the complicated one. And if you would imagine like an agent that could then use the ontology in order to find the right way to compute the similarity between two of these densities of states, for example, then I could use, then I could have this computation that I would like to have. It's just apparently hard to implement that or have that.
So actually, this is very much connected to the original vision of the semantic web, which was proposed in 2001, where the idea was that you would use ontologies, and you would use knowledge representation languages where the databases could represent what their capabilities are. So what is the content that they have? For instance, this database is about this kind of materials. It has these kind of properties stored. And these are the relations between these properties. And then you would have agents, exactly, that when we have a query or a need, would actually try to figure out which of the databases to use, translate the terminology that we have used for the query to the terminology of the databases, get partial results from the databases, and then merge this into a full answer to the question.
I mean, you now, also you referred to this was the initial idea, and this was in 2001. So my question would be, is it realistic? Also could this happen, or was this just a fantasy in the beginning?
I think a first step has been made to this by, for instance, the biomedical field. Quite many of the databases there are annotated with ontologies. Mm-hmm. And this makes it easier to find which databases you need. To get information in the databases, there are some databases that allow you to actually use the ontology, click on terms, and then immediately send a query to the database with the ontology terms. So steps have been made in different fields towards this, but the full vision has not been realized. That's clear. And the vision of semantic web was actually redefined a few years ago, where there's more of focus on a web of data, where ontologies are still important as the way to structure the data, but more focus is put onto data on the web that is linked in different ways.
In view of the time, I would like to end the discussion here. I would like to thank Patrick, Karsten, Giancarlo very much for their contributions today. Appreciate it a lot, and I'm sure that there will be much more to come in this field. And let's give them a big hand and applause from the people here in Louvain.
Thank you very much. It was a pleasure. Thanks for the invitation. It was great interacting with you all, Patrick and Karsten and so on. Hope to have more opportunities in the future.